Hi, welcome to Dissolve Chemistry. In the previous video of thermodynamics, we have discussed regarding expansion work. In that expansion work, we have seen first one as free expansion, where we derived W is equal to 0. Okay. Then the second one, what we have discussed, work done in expansion of the gas at constant pressure, and we derived W is equal to minus P into delta V for a noticeable change in volume. Then the third one what we have seen is that is work done in reversible isothermal expansion of the gas. So and we derived an equation minus nRT ln V2 by V1 or P1 by P2. Okay, so today we will discuss regarding adiabatic expansion work. Okay, adiabatic expansion of the gas. So prior to going in detail with what is adiabatic expansion, let me know what is adiabatic process. The process which is carried out, say for example, we have to take an completely isolated system in which 1 mole of gas you have to assume being packed and fitted with weightless frictionless piston. So then we are going to allow that to undergo expansion. So we will see that one, that how actually adiabatic system is going to be there. See here, see for example it is like this. Okay, a perfectly insulated wall, which we also is known as adiabatic walls, right? So where Q is equal to 0 means neither heat enters into the system nor heat goes out of the system. So therefore there is no exchange of heat as well as matter with the surrounding. So therefore such system we call it as what? Adiabatic system. In such system, when you allow the gas to expand, right, then it has to expand with what? See here, gas is packed, no heat is entering into the system, and we are allowing this gas to expand, meaning is it has to expand with the expense of its internal energy. So we know that first, according to first law of thermodynamics, Q plus W, and we know that delta U is equal to Q is 0, so plus W. Means whatever the work system does, that has to be done with the expense of the internal energy. Now suppose if you compress the gas, if you change the volume, means negative change if you do, then what happens? Your internal energy will increase. Okay, so now we will go by one aspect, that how the different thermodynamic variables are going to change in adiabatic expansion. Now suppose first we will see change in internal energy during adiabatic expansion, how internal energy will change, delta U. Okay, so now already as it has been mentioned, so whatever the work if it does, such as expansion work, it has to do with the expense of the internal energy. So therefore we know that from molar heat capacity at constant volume, Cv is equal to du by dt at constant volume. So therefore the change in internal energy can be given as Cv into delta T. So that is what we can get. The change in internal energy is equal to molar heat capacity of the gas at constant volume into change in temperature during that expansion. Okay, so when the gas expands, so then whatever the change occurs in the temperature, because obviously when the expansion takes place, that too with the expense of the internal energy, then what happens? The temperature of the system is going to decrease. So that we will derive and we will prove that one. Okay, so this is what is change in internal energy. Now we will talk about second one is change in enthalpy during this adiabatic expansion. Enthalpy change we will see. So the enthalpy H is equal to U plus PV. So change in enthalpy means delta H is equal to delta U plus delta PV. We know that for ideal gas, PV is equal to RT for 1 mole. So therefore, if we substitute this, okay, here, so then it turns out to be delta H is equal to delta U plus R delta T. Okay, so then we know that what do you mean by delta U? Substitute the value of delta U here, CV into delta T plus R delta T. Okay, so now delta H is equal to, you take this delta T outside, then it will be CV plus R into delta T. Right? So now CV plus R, we know that CV plus R is equal to CP. Molar heat capacity at constant pressure is equal to molar heat capacity at constant volume plus gas constant. So therefore delta H is equal to, what is turns out to be Cp into delta T. Okay, so that is how we determine. Then the third aspect is work done. Already we know that third one is work done in adiabatic expansion. Okay, so W is equal to, already we have said delta U. So therefore work done will be what? Minus delta U, expansion work it is doing. So therefore there will be a decrease in internal energy. So the CV into delta T. Right? So therefore we will write all three equations. Right? So we will write here. So delta U is equal to, during adiabatic expansion, CV into delta T, and delta H is equal to Cp into delta T, and work done is equal to minus CV into delta T. So in all the cases, means change in internal energy, change in enthalpy, work done, all are going to depend upon how much amount of the temperature is changing. To what extent temperature is changing, means what is the final temperature if we come to know. Initial we know that what is the final temperature if we determine, then all the other changes we can determine. Okay, so now, so we will see this change in temperature, or what is the final temperature we will determine. Okay, so by using adiabatic expansion reversibly, the gas expands adiabatically and reversibly in such condition. So what is the final temperature we can determine, right? So now let us consider W is equal to work done, or we will write directly. Already we know that one, delta U is equal to minus W, because Q is 0. Expansion work it is doing, so therefore negative sign work. So therefore delta U is equal to, delta U is equal to minus P into delta V. So we will say initially we will take small changes. Du is equal to P delta V. Okay, so now we know that du is equal to Cv into dt is equal to minus P into dV. So from ideal gas equation, P is equal to RT by V. So let us substitute that. Cv into dt is equal to minus RT into dV by V. Now let us take the temperature over here. So therefore Cv into dt by T is equal to minus R into dV by V. Okay. So now substitute what is R. We know that already we have used that Cp minus Cv is equal to R. So that we will substitute here. Cv into dt by T is equal to minus Cp by Cv into dV by V. Okay. So next what we will do, Cp minus Cv, suppose this Cv if we take on to that side, then it turns out to be dt by T minus Cp by Cv minus 1. Okay, I hope you have understood. Cp minus CV by CV means CV get cancels, but therefore it remains 1, and here CP by CV. So now CP by CV we will take it as what? Rho. Okay, let us take CP by CV as is equal to rho. Okay, ratio of molar concentration at constant pressure and molar concentration, molar heat capacity at constant pressure, molar heat capacity at constant volume is equal to rho we have taken. So into dV by V. Okay, so therefore CP by CV we will substitute as rho. Right? So then we will see that, let us integrate between the limits, that is initial temperature as T1 and T2 and volume, initial volume V1 and final volume V2. Integrating above equation under the limits T1 and T2 and V1 and V2. So therefore T1 T2 dt by T is equal to minus rho minus 1 into integration of V1 V2 under limits dV by V. So which turns out to be ln T2 by T1 is equal to minus rho and ln V2 by V1. Okay, this we can write as minus ln V2 by V1 raised to the power rho minus 1. Then next is ln T2 by T1. So now ln, let us cancel it. Bring this minus sign this side, so therefore it turns out to be T1 by T2 is equal to V2 by V1 raised to the power rho minus 1. Okay, now if rho is greater than 1, if rho is greater than 1, then final volume will be greater than initial volume. Therefore, your initial temperature is greater than final temperature, or final temperature is less than initial temperature. Meaning is what? As the gas expands reversibly and adiabatically, means as the volume increases, no heat is entering into the system. Of course, it is an adiabatic process. So therefore, as the gas expands and volume increases, then what happens? Volume cools down. Meaning is what? Temperature of the final temperature of the system is going to decrease. Okay, so that is what we call it as final temperature decreases, and we can determine, suppose if we know the final volume, initial volume and initial temperature, we can determine final temperature. Similarly, we can bring out the relationship between pressure and temperature also. Now let us talk about the final temperature. We can also calculate by bringing relationship between pressure and temperature in reversible adiabatic expansion of the gas, right? So let us take, we know that P1, right, P is equal to, or PV is equal to RT. So V is equal to RT by P, right? Now suppose initial volume, if it is V1, then T1 P1. Similarly, if the volume is V2, so then RT2 by P2. Let us substitute V2 by V1 in the given this equation. So therefore T1 by T2 is equal to V2, let us substitute RT2 by P2 into P2 by RT1 raised to the power rho minus 1. So now P2, so this R get cancels, then what it remains? T1 by T2 is equal to T2 by T1 into P1 by P2 raised to the power rho minus 1. So now segregate these two and then bring on this side. So therefore T1 by T2 into raised to the power 1 T1 by T2 raised to the power rho minus 1, which is equal to P2 by P1. Here only we will change it, 1 minus rho. Okay, so now this is plus 1, this is minus 1, get cancels, it will be rho. So therefore it turns out to be T1 by T2 raised to the power rho is equal to P2 by P1 minus rho, 1 minus rho. So this is how we will bring the relationship between temperature and pressure. If we know the initial and final pressure and initial temperature, then final temperature also can be determined by this equation. Okay, so we have seen the various, because why the final temperature is important in adiabatic expansion. We know the initial temperature. What is the final temperature? If we come to know that one, then we can calculate all these factors: change in internal energy, change in enthalpy, work done by the system. Okay, so all that can be determined. So I hope you have understood the various aspects of adiabatic expansion of the gas. Thank you for watching. Okay.